Hello, AP Chemists! It is now time to start our kinetics unit. So we've already talked about thermodynamics, and those things are still going to be at play here. But now we're going to kind of zoom in and look at things on a particle level and talk about different factors that would affect the speed of a reaction. So remember, I've talked about, favorability. Does a reaction happen? And we've talked about barriers that could be there that could keep a reaction from happening. And so now we're going to look at some of those barriers. Okay, so most reactions do not occur in one step. In fact, they usually occur in a series of two or more steps that we call elementary steps. So it's like one step happens, then another, and then another, leading from our reactants to our final products. Let's think about why this is true. For an elementary reaction to successfully produce products, reactants must follow three conditions. So there are three things that I always want us to consider about a collision to think about whether it's going to result in products or not. Okay? The first is the reactant particles have to hit each other, right? They have to collide. If they don't collide, the reaction doesn't happen. Okay? The faster they collide, the more they collide, the harder they collide, the more successful collisions we are going to have. Okay? More collisions occur when we have more stuff, when the concentration of our reactants increase. So we can think of that as having more particles or more stuff that are able to hit each other. I should probably take off my ring because I'm going to hurt myself. Okay? Also, the surface area of the reactants is also going to increase the number of collisions and therefore the rate of the reaction, right? So if there is more space, or not more space, if there are more places for the collisions to occur on this surface of the sample, then you are going to have a greater rate of reaction as well. Okay? Also, if you increase the temperature, things are moving faster, they're going to hit each other more. Okay, so here is my surface area example. Okay, we can see that there are more collisions here when you have high surface area versus here where you have low surface area. So more collisions that way. Okay, so collisions have to happen, but they also have to hit each other in the right way. So let's say that I have a reaction between two things and they have to hit this way. Okay, they have to hit this way for the reaction to occur. Okay, if they hit this way, reaction doesn't occur. If they hit this way, reaction doesn't occur, right? They have to hit with the correct orientation. Otherwise, collision not successful. So here I have an example reaction. We have the two molecules, and like I said, they have to collide in the correct way. So if we see the reactants in the products, we see that what really is happening is this bond between the nitrogen and the bromine. So this bond between the nitrogen and the bromine is breaking. Okay, so in order for that to happen, and also we see that a bromine-bromine bond is forming, right? So in order for that to happen, the bromines have to hit each other. To form a new bromine-bromine bond, two bromines have to come together, right? So if two bromines don't hit, the reaction doesn't happen. So we can see right here that the two bromines do hit each other. Okay, so they do collide with the correct orientation and form a new bond, and then the nitrogen-bromine bond breaks, and so that is a correct orientation. However, in this reaction, we see that the oxygens are going to collide with each other. Okay, that is not going to cause the bromine-bromine bond to break because the bromine-bromine atoms are not hitting each other. Okay, so they have to hit. They have to hit with the correct orientation. The third requirement is that the collision has to have enough or sufficient energy to overcome the activation energy. So we've looked at reaction profiles, and we know that to get a reaction to start, we have to break bonds, right? If there's not enough energy to break the bond doesn't break and the reaction doesn't happen. And so the greater the percentage of collisions with sufficient energy that there is, the faster the reaction is going to be. So you can imagine, maybe that bromine, like in the example above, the bromine and bromine come together, they hit correctly, but they didn't hit hard enough. There wasn't enough energy. If that happens, the reaction doesn't occur because they have to hit with the correct orientation, and they have to hit with the correct energy, okay, or enough energy, more than the activation energy, okay. So the major point of emphasis here is that when the temperature is increased, the reaction rate is going to increase for two reasons. So this is actually really important and you're asked to describe this quite often, both in this class and just the AP test, because it really shows knowledge of what's happening, right? So when the temperature increases, the particles start moving a lot faster, right? When they move faster, they hit each other more. That's going to increase the rate of the reaction, okay? If they're moving around faster, they have more energy, right? Because we've increased the average kinetic energy by increasing the temperature, then more collisions are going to have enough energy to overcome the activation energy. So both of those factors would be at play. So you could think the opposite would be that if the temperature went down, there are fewer collisions, right? Because they're moving slower, right? They're not going to hit each other as often. That lowers the rate. And then also, fewer collisions are going to have enough energy to overcome the activation energy, right? They're lower energy. So when they hit, the bond may not break because the activation energy hasn't been reached. Okay. So I mentioned that reaction profiles are important to think about with kinetics, and we're going to look at these really throughout the whole unit. But you should be able to look at this reaction and tell me something, or this reaction profile and tell me some things already. Okay, you should be able to tell me, for example, that this is an exothermic reaction, and I know that because heat was released to go from the reactants to the products, right? There's less energy in the products. Okay, so I wanted to label a few things that are on here, mainly just what different things are. So the y-axis is our potential energy or our energy. Honestly, you should probably pause. You should probably pause me and write all these out yourself and see if you get what I get. Okay, the x-axis is already labeled as the reaction coordinate. You can also think of that as the progress of the reaction. It also asks us to label the activation energy, which remember is the energy required to start the reaction or the energy to break the bonds of the reactants. So here, it's going to start at the energy of the reactants, go up to the top of that bump, and that is my activation energy, which I represent with a E, capital E sub A. Now, in terms of discussing how this relates to successful collisions, higher activation energies mean less collisions, less successful collisions. Lower activation energies would mean more successful collisions because more collisions would have enough energy to overcome that activation energy. Okay, for our delta H, remember that is the difference in energy between the reactants and the products. Remember, we calculate that by doing final minus initial. Okay, and then something we haven't seen before is this transition state. So basically, we have these two reactants coming together. Okay, so we have these two reactants that are coming together. They're going to collide in the correct orientation. And what ends up happening is, I'm going to change my color. This new bond is going to form And then this bond is going to break. And you don't have to understand the molecular orbitals or the chemistry that explains why that happens. But basically, this is that middle, kind of the not intermediate. It's kind of just that middle state, that transition state where the new bond is forming and the old bond is breaking. Okay, so that transition state is at higher energy. Okay, that transition state is not stable, and then it comes down and we form our products. Okay, so we can see our new bond that formed to form that product, and then we broke a bond and that kicked off that red sphere, okay, which was a bromine. Okay. All right, so we've seen a Maxwell-Boltzmann distribution already as well. I just wanted to relate this to kinetics. One thing that I did want to point out is that this is speed down here. I should have found a graph instead that had energy. Okay, so obviously these numbers aren't going to necessarily correlate correctly with energy, but the graph is still going to be the same basic look. So just some reminders from this already. When we increased the temperature, we saw that the curve flattened out and that the peak moved to the right. And so those are things that we should see already. We can see that, okay, I'm going to draw in something here. I'm going to draw in an activation energy. Okay, so that is going to be an activation energy. So that would be the energy that's required, right, for a collision to be successful. So if I look at what I have here, for at 300 Kelvin, I'm going to do it a little different. At 300 Kelvin, those are my only successful collisions, right? If I increase my temperature, more of my products or more of my reactants have enough energy or have more energy. So when they collide, there are many more successful collisions. So we can see that increasing the temperature would increase the number of successful collisions. Now, if I were to add a catalyst, that is going to lower my activation energy. If that lowers my activation energy, then I can now see that I would have more successful collisions at both temperatures, right? So I would see that my number of successful collisions has overall increased, okay? And you can go ahead and go in and write this. I'll go through and I'll post this on Canvas so that you can see my explanations. I just don't want this to go long, but you can also rewind me and see what I was saying. But basically, if you increase the temperature, then there are more collisions that overcome the activation energy. If you lower the activation energy, then there are more collisions that have sufficient energy to overcome the activation energy. So just as a reminder, the three conditions that need to be met for a reaction to occur is they have to collide, they must have the correct orientation, and they have to have sufficient or enough energy to overcome the activation energy. And so we will look at several reactions and we'll talk about that as we go through and progress through this unit. The last thing that I wanted to mention is the Arrhenius equation. You are not going to have to do a single calculation with this equation, okay? You're not even going to be given this equation, but there are some relationships that this equation is going to show, and that is going to help you understand these relationships or see it mathematically. If I were to plug in activation energies, so if I were to plug in activation energies here, as that number increases, I'm going to solve for K, which relates to my rate of reaction, and I'm going to see that the rate of the reaction is going to go down. So if I increase my activation energy, then the rate of the reaction goes down. You need to know that relationship. Okay, you also need to know the relationship between temperature and rate of reaction. If I were to increase this temperature, that's going to increase the rate of my reaction. And you can plug in different numbers into these and see that that is true. Okay, that is all that I have for you. So we've started our talk about kinetics at a very particle level, and we're going to build up from that and talk about rate of reactions, talk about reaction mechanisms, and really just really dive in and see what's affecting rates of reactions and how we can calculate those. All right, bye y'all.